figurehead.
This meeting is being recorded.
Go ahead, Mohamed. We're ready.
Okay, Sergey, thank you very much. So today we will actually go through the paper Moving Deep Learning into a Browser. How far can we go? This paper actually by Yamma and other authors in 2019. And actually, when we talk about the browser here, we talk about the client side. Do we really need to utilize the advantage of develop our application on the client side of the browser? Do we really can find any advantage of that? So if we look in the main actually advantage of that, we will bring in the beginning here some important advantage. One of them is actually the portability. So creating a tool that is cross-platform and can be also able to run on heterogeneous development environments is actually an objective and a target. And this is actually one of the things that browser can bring it to us, because you only, with JavaScript, you only program one and run everywhere. And this is actually true since your application actually is within the resources limits that is there with the browser. So the portability here is actually a big feature. And the other one actually is that you are doing like an edge computing in this case. So we have a peace of mind in terms of server setup, server install, server troubleshooting, server is down, all these things actually is not there. You are coming close to the client. So the client actually here have the privacy, have his own or her own resources on the machine, and you are deploying these resources to run your application. So you are not actually having any costs in terms of server setup at all in this case. And this is actually another objective here. The thing that, as we said before, we are not talking here about an application that have any server at all. The application that have servers on the internet or in the browser are many actually, but we are talking about the client side specifically.
So and in this case, can you talk to what is edge computing again? Because like it looks to me that my understanding is different. What
we have something sharing here. So edge computing, you are coming close to the client. The client actually here have a privacy and timely response. You are working on the edge of the client.
Is it like client side computation?
Yeah, what is it called edge then?
I think it's because you have like a central, if you have a central node that you have to send data to and do computing there instead of on the nodes. If you do it on the nodes, that's edge computing. Like if you have traffic predictions, like you can.
How is it? On the node is what?
If you do it on the nodes instead of in a central location, sending the data and then doing it on the central location, that's edge computing, right?
It's kind of like a leaf node, basically.
Yeah, exactly. Doing it on the leaf node is edge computing. That's what I generally.
Oh, okay. Because I thought edge computes, but
if you have traffic with cameras, instead of sending the whole feed to a central node and then computing something there, you can also do the computations near that camera, and then only send the data that is left over after the computation. That's edge computing.
I can see how that would offer some privacy. Like you don't have to send like your personal data. You just send
exactly. If you send the number of cars that's on the traffic web camera instead of the live feed, it's more privacy preserving because you don't know what cars or like what their license plate is. You just know that there's.
So the word edge comes then from imagining an octopus with a lot of
I think it's from
sensing on their like edges of that animal. Okay.
And that's also why it's often on embedded devices, because that's what people generally also use it.
Yeah, I always thought about embedded devices.
But it needs to be embedded if it's on the node, because nodes are generally a very small computational, like they have very resource constraints.
That's how I thought the edge comes from, because it's your resources are on the edge of possible or enough, but barely enough on the edge.
I think both are kind of fused together into the.
Oh, okay. Well, it looks like you're using different definition now than I was totally into the other kind.
This kind of reminds me of like the mobile agent paradigm, where like basically you either bring your processing to the data in the center, or you bring your like agent to the data. I don't know, like you.
Right. I mean, implicitly, embedded devices by themselves are, the whole point of them is to do that like non-central computation. So in a way, those definitions do fuse together, because embedded devices kind of have that same definition built into them as well. Like that they're more close to the user, but also just close to like where the data is like accessed stuff.
Yeah, so browser is like that device, because that the application we spend most of our time in.
Right. Although even bigger edge computing would be if you do it at the MRI scanner, right? Like instead of, that would also be edge computing.
Not in the modern world, because MRI scanners are owned by companies, and
No, sure. But if you do it like in the hospital, like at the scanner itself, that would also be edge computing.
Yeah, that's an interesting idea. You know, there are open source operating systems for routers. Let's write one for scanners.
Right.
Okay, sorry. That's taking us like. Yeah, I usually do that. I'll try. Continue, Mohamed. Sorry about that.
Yeah, no, that's fine. So actually, I didn't find actually something that can be very close to that, because if we said a client side, that maybe people confuse that there is like a server side, and if we said serverless, for example, this is a new term. Nobody actually can be comfortable with it. So I found that edge computing maybe the most thing that we are talking about. We are talking about all the computational in the side of the client here, no server at all. And this is actually something that have a big advantage, because once you have a tool like that, regardless of how many users are using simultaneously, it doesn't make any problem with you. You have actually a distributed computational in this case. Everyone on it's in his or her own machine. And this is actually one of the main advantages in this case. And if we also talk about the browser side here, we can actually doing something that browser can offer to us, that the browser actually can actually utilize the integrated graphic cards in this case, which is the thing that native platforms like TensorFlow or PyTorch or whatever cannot do it unless you have a standalone graphic card in this case. So this is one of the advantages that actually we can actually also utilize it, and by using WebGL or WebGPU, in this case, we can actually accelerate the performance in this case in the browser than the CPU that actually can be utilized with other platforms or other frameworks, sorry. And then also we have this privacy and time response for the client in this case. So these people actually trying to find, because we are not aware about all the size of the browser, there is some hidden information. We are not actually knowing exactly what could be the limitation of the browser until we are making some experiment in this case. And this paper was one of the first empirical study in this area. You can be like, people can actually run like a model or a machine learning actually application. They have a huge RAM in their devices, and they don't actually know why actually the browser complaining that there is no enough memory to run the process or run the task. This is because there is a limitation for the browser itself. So we actually want here to know what could be this limitation and how we can actually utilize the maximum benefit from running into the browser in this case. So the main question that the author's trying to answer here is what features do existing framework provides to implement various kinds of deep learning tasks in the browser. So how many frameworks actually we have and what they are offered to us. And we will see actually they make like a survey here to answer this question. The other one is how well do existing frameworks perform over different deep learning tasks. And they actually separated these tasks in training and inference task mainly, and see the response of the browser in this case. And the final question they was asking is how big the difference or the performance gap between the deep learning in the browser and in the native platform. So once you are trying, for example, TensorFlow, JavaScript, is there a big performance gap between this framework and the native one, the TensorFlow itself? So in order to answer the first question here, they make like a surveyed analysis to see what is the tool available and what is the functionality and developer support that tool is offering. And in this case, actually, they focus on 7 popular JavaScript-based frameworks. You can find them in the first row. So they are using TensorFlow JS and Convnet JS, Keras JS, Web Deep Neural Network, and Brain.js, Synaptic, and Mine. So some of these actually frameworks are not supported anymore. I mean, some of them are not active. Some of them is still active, especially the TensorFlow JS and the Web Deep Neural Network. They are still active. And when this paper published in 2019, actually, they actually didn't at that time get all the supported layers and the supported activation layers and optimizer types that we have now with these tools. So they are actually increased much more than that time. And we can see here, for example, that not all these tools actually have a supporting for WebGL. Not all of them have a supporting for saving the training, or even some of them don't even give you the option to train your model in the browser. And in terms of their size, actually they have a different size. The library have different size. And we can see, for example, Convnet here have a very small size, 33 kilobytes. And this actually will have some impact on the performance later, as we will see. And others actually have a bigger size because actually they are more comprehensive. So TensorFlow JS, for example, here is considered like a general purpose one that you can actually, with it, you can make or create different type of tasks for the deep learning. The others are more limited. And we also can mention here that not all of them maybe support WebGPU, which is actually like the next generation of WebGL.
Can I comment something? This table looks large, but it's not comprehensive. There are many more libraries that are interesting, like Onyx is not there. Onyx is interesting, but we couldn't get it to work for our case because not everything is implemented. Then there is a library, I forgot the name of, that implements stuff in WebAssembly. There's that thing. It's in WebAssembly and GPU and everything. So people went really deep into, like, it's not just that. We'll use JavaScript and build layer by layer like an onion. They really grokked it. But unfortunately, again, not enough, I guess, user base or developers, so not all the operations are implemented. It didn't work for our library. So there are a lot of efforts, but they're kind of depleted in contributors, I think. TensorFlow, JS, of course, there's Google Money, so they can just point a developer to work on it. But other open source projects, they need developers. Okay, thanks.
Yeah, so only, yeah. They actually make like 7 only for their survey at the time, and this is actually was also maybe like 3 years ago. So there is more technology come later after that paper. Starting from the first for their experiment setup here, so they are starting to actually create a very basic model, just a fully connected deep learning model for MNIST data set, and they trying to actually to try the performance of this model with different number of hidden layers and different weights of these hidden layers. So they have like 1, 2, 4, and 8 hidden layers as a configuration to try. And also they actually change the number of neurons in the range from 64 to 256. They all the same platform here have been used, the laptop, and 2 type of graphic cards here have been used, the integrated one and the standalone one, the NVIDIA 1070 for the same operating system, Ubuntu, and the same browser Chrome. And the first results for the training time here, we can see here like with these different configuration, there was like different responses. Some of them make sense. Some of them actually can give us like some information about the hidden parameters that we are trying to figure out in the browser. So for all of these testing parts, you can find that increasing in the network size, the depth or the width or both, can increase the training time. So here, the model complexity, this is actually makes sense, but for the CPU-based framework, like the ConvNet.js or BrainJS, or even TensorFlow.js with the backend in the CPU, we can find that the ConvNet here have the best performance. Actually, this is mainly maybe because the ConvNet have a very small size, and also because TensorFlow its main advantage is not in the CPU, but in the GPU much more with the WebGL.
Why did they stop it?
I'm sorry?
They stopped supporting it, right? That's one of the projects that stopped supporting.
TensorFlow is
No, ConvNet.js.
Oh yeah, this is actually stop supporting. The only one he's still supported here, I think could be like BrainJS and TensorFlow. So let me, oh yeah, BrainJS is still active, but ConvNet.js is not supported anymore.
Yeah, but it performs better, so that's kind of...
And yeah, so in terms of GPU now for the integrated and for the standalone, the NVIDIA one, actually we can see that the performance is much more almost stable with the different model complexity we have. And this is actually because maybe we didn't reach the computational bottleneck of the GPU in this case. It's a very small model according to the power that the NVIDIA can offer for this experiment. But we can note here also in the last 2 charts that there is a significant increase in the integrated GPU, because actually integrated GPU is much less powerful than NVIDIA one here. So still NVIDIA is stable while the integrated one actually have much more delay. This is for the training in general. So they also doing like a model loading time. And in this case, actually, we can see here, they also tried for the web deep neural network in this case. So we have the CPU performance above and the GPU performance in the second chart. The size of the model here is given. So in general, for the CPU backend, we can see that the loading time of different models of the same network, for the same network, or for the same framework here, is actually proportional to the size of the model when it increases. The more you increase the model complexity, the more the loading time we can have for loading the model for with all these frameworks. Still, ConvNet here on the CPU is much faster than the others, and for the we can see that for the GPU here in this case, still the TensorFlow is much better than Keras and the Web DNN. For both, actually, for the integrated and the NVIDIA one. Actually, when we come to the inference time, how long it take for making the inference here, we still have also, we can have also some interesting results. So if we talk about small size model, we can see that ConvNet here is the best one. And for the Web DNN here GPU, actually we found that the Web DNN GPU is more slower than the Web DNN GPU in this case. And this is actually interesting, which actually makes sense, because in some model size that is small, we are talking actually here about JavaScript and browser, which is a single thread. The engine actually is a single thread. So we utilizing in many cases actually one core, especially when we come for a very small size model. And this is actually CPU in general as a single core is much powerful than GPU single core when you use it. And in this case, actually, we also see that the performance for the web deep neural network here is actually also worse than Keras.js. Keras.js actually was, I guess, Keras.js is the one that TensorFlow.js is based on later. So until this moment, maybe there was both separated, but once Keras.js become absolute, that's because all the efforts come to TensorJS, which is based on it. We can see also for TensorFlow.js here, it can have much better performance with the smaller model on the CPU than the GPU. And also for the bigger model, he has better performance on the GPU than the CPU. So there is no mention for the paper here for the part that when we use Web DNN for the Web GPU, which is actually the new generation that it actually should give us a better performance than the WebGL itself. But I found like a metric here can show us this performance when we use the Web GPU. In this case, it actually it outperformed Keras.js. Even our Keras.js in the WebGL was better than the DNN WebGL, but for the WebGPU here, it's actually outperformed the Keras WebGL in this case. But WebGPU actually is not as is a new technology that is not exist in every browser currently. The plan is to dominate and replace WebGL in the near future. WebGL actually has a technology. When you use it, you will have an overhead. You have to create a programming, not a programming layer, but an interface that make you able to use the APIs of the WebGL, because these APIs was specifically created for graphics application. So if you want to use it for a general purpose, actually it is hard to make that unless you create your interface of functions to utilize this in the background. So this overhead actually have a cost in the computational. And this is why WebGPU they come to overcome this problem, to make you able actually to utilize additional number of APIs, make utilizing the GPU here in this case, giving you a general purpose ability to create your task.
What does the browser have to do to get these? Like, does this only work in Chrome or Firefox, or like, is it pretty widely, like, do they work across platform pretty, like how difficult is it for the browser to go to a website, have the same experience across platforms?
Do you have any question? Because the sound is a little bit far.
Was that not clear?
Mm-hmm.
How similar is the experience across browsers for each of these different things? Did they talk about that?
Oh, yes.
Do you have any personal experience with that?
Yeah, this is actually, not all the browsers have the same capability. I mean, there are two close to each other, like Chrome and Firefox, which I think they have like, they look into each other to copy the features. But with WebGPU, for example, there is a special version of Chrome that can make you able to utilize the WebGPU, but there is no similar version in Firefox. This is something that actually you can find. This is actually something that for now is a big difference. In terms of the memory limitation, because you can have like a RAM that can be a big RAM, like 16 gigabyte or something, but the browser itself is limited. It can be maybe not able to utilize more than 1 gig RAM or 2 gig RAM, and then it raises for you an issue when you have a task that consume more than that RAM, which will make you maybe sometimes confused because you have the enough RAM. But no, the browser have a certain limitation, or it's a specific limitation that this actually empirical study come to maybe like figuring out what this limitation can be like, because we don't have a lot of information about this limitation actually. So it's depend on some browsers, when they come to the term of maximum, for example, for the WebGL, when it comes to the term of the maximum texture size that you can actually allocate or create, they can be different. One of them can create up to 1 giga, one can create up to 2 giga, and so on. So this is actually will affect if your task will be run, or it will raise a memory issue. And the memory issue is the most common issue actually. It comes to your browser when you are trying to allocate enough memory to your task. And in our case, in our very special case with Brain Shop, we actually doing like it's a tensor of 5 dimension, which is not something that all the browser can actually perform. And when we are trying to allocate the memory for that, it was like we need to make a series of workarounds to try to manage the memory in our own. So we making like disposing every time, disposing for what we just finished from a second or from the previous step, in order to make the memory that we need to the second step is available, so we don't go to the issue that it is expected with these dimensions of tensor and this volume we have as MRI. So this is actually one of the things that we found some difference between the browsers in this case, but in general, the difference wasn't that big, especially for between Edge, Chrome, and Firefox. I noticed that Firefox maybe is better in some cases and Chrome is better in other cases. And this is actually just from the experience. There is nothing there is no documentation can telling you what exactly you can expect in every case, I mean.
So I just have one comment about the browsers. There is kind of a fake diversity in the browsers, right? We know that there are only 2 real engines, the Chromium engine that most of the browsers are using with modifications based on that, and Gecko that's developed by Mozilla that Firefox is using. So there's really no diversity. We're getting this situation when you go to supermarket and you see variety of brands, but they're all owned by Coca-Cola. Like I'm exaggerating. So this is very bad for our technological development. Just a minute of politics. Sorry, it's just because we need different experimentation. Just like in science, we need different ways in different. Firefox is not worse than Chromium. I'm on Chromium myself, guilty. On Brave because it is faster and Firefox doesn't have enough developers to just do the radical thing that Chromium has done, turn off JavaScript or like turn off all of that stuff and not getting some little things. And then it's instantaneous because it doesn't have to contact many sites it contacts otherwise. But just have that in mind when you're choosing or like when you're seeing the diversity, it may be just fake diversity. Sorry. Because I mean, this is a pain point. We need experimentation, different engines, different things, different operating systems. Okay, go ahead. Yeah.
Yeah. So for the last part of this experiment, they trying to actually make a comparison between the native TensorFlow and the TensorFlow JavaScript or JS, which actually is something that can show you some unique advantage of the browser in this case. In general, when you don't have a standalone graphic card, in this case, if you run in your desktop application, you will run on the CPU. And in this case, you found here, for example, that the TensorFlow CPU is actually much slower than TensorFlow JavaScript that hasn't an NVIDIA card or standalone card, because JavaScript here, in this case, the TensorFlow JS is using or utilizing, the browser utilizing the integrated graphic card. And the integrated graphic card is something that exists in all machines now. It's actually by default there. But only browser is among the few who can utilize this in the computational in the browser. And in this case, you can find that TensorFlow JS, without a standalone graphic, outperform TensorFlow in the native environment or TensorFlow on the desktop. Also, we can see here that the TensorFlow with the NVIDIA graphic have almost the same performance as the TensorFlow.js WebGL. So they are similar if there is a standalone graphic, and the TensorFlow.js much better if there is no standalone graphics, because it utilizes the integrated graphic card in this case. Here actually, they tried that for like 5 different models. So they tried with MobileNet, DenseNet, Exception, Inception, and ResNet. And some other models didn't run like VGG because it raises a memory issue, like we said before, during the limitation of the browser. This limitation should be in the maybe in the near future to not be exist once the web GPU will be more dominate. So in this case, actually the AI community in general, there is a feedback between the browser vendors and the developers that there is a promising results, and this promising results actually we need to spread the overcome this shortage, the current shortage, and they actually taking this seriously to overcome to improve the current technologies and to speed up the spreading of web GPU as soon as possible. So the last thing that they are trying to do in this paper, actually, they make like a decision tree analysis, and they just want to find out in a very simple model, how to figure out the most important feature or the most important factor. And they found that, of course, being utilizing GPU or CPU, this is the most important factor. And make a difference between the TensorFlow.js and TensorFlow when we are taking the execution time ratio in this case. So they like for the case of the CNN here, they just telling you that when you see like in the last or in the leaves, in the bottom, when you see like there is a factor of 1, that means both of them have the same performance. So it's up to you to what to do with your application. Would you like to go in this case to the browser or your desktop, because both will have the same performance. And they both like what condition that this performance be the same, what other condition that this performance will have a very huge gap. And we see that in some cases, actually, we can have the same performance. So what we can take away from this study is actually, we have here some notes that can come for the application developer, others can come for the framework, deep learning framework vendors, other for the browser vendor. The main point here that actually some frameworks are still limited, not all of them. But I guess for up to date today, I mean, TensorFlow.js and Web Deep Neural Network are doing good. They have now more comprehensive framework, more comprehensive libraries, and they are going actually to almost be like a general purpose frameworks for any application you want to do. When you are like, they give a recommendation for the developers when you are trying to design your own model, just give attention to the width of the layer. you are using. They are talking here about the fully connected just as a simple model they are using. So they found that the weights or the number of neurons are affecting the performance of the browser in this case. The TensorFlow actually JS, when it's run on the NVIDIA card, is competitive as a performance with the TensorFlow itself, TensorFlow, not JS, the TensorFlow native one, that is also run on the NVIDIA cards. So both of them in the inference have almost the same performance. And we mentioned before the importance of the integrated GPU, which is a unique feature in the browser that actually when you run your deep learning model in the browser, it will automatically, the browser will utilize this for you, and it will give you much better performance than any other framework that only use a CPU. So this is all the marks, most of the important marks we have till this end of the paper. And if there is any question about that, we are now almost covered everything they concluded. And I guess this is one of the first empirical studies to learn about the limitation of the browser. There will maybe some other papers come later about also addressing the same issue, but in different way. But I guess this is actually like a point for the main actually important factor in the browser that can affect your decision when you are trying to use a browser, and it can give you like a motivation for the main need for you, that you will actually trying to create your tool in the JavaScript rather than any other language. Any question?
Anyone? Questions, thoughts, points?
This is a reference for all these tools. So I guess in the end that yeah, if we talk about why there is a need for the browser for doing the deep learning or machine learning or image processing in general or whatever, this actually will have its impact on that you are addressing a tool that exists everywhere in every operating system. In Android, you don't need actually to worry about any server here set up or troubleshoot or cost or whatever, and you are addressing the most or you are doing like a marketing for your tool. This is actually where all the audience or the browser is where most of the users are there. So it's very simple in access, very simple in trying, and you just trying for doing like a marketing for what you are doing. It's just simple to be used, simple to be accessed, and this is one of the major actually advantage for the browser. That's why they are actually trying all these steps in order to make it actually be able to carry out all these machine learning or other related application.
Yeah, thanks, Mohamed. I agree with the marketing part, although I mean it's not just marketing; it's ease of getting to the user. It could be interactive or anything, but you can get feedback really quickly because the users don't need to install anything, and that's very important in any corporate environments, especially because you cannot install stuff and things like that. But I don't agree about right once, right around everywhere, because especially in deep learning, when we are pun intended on the edge of what's possible with hardware.
Yeah,
the browser is a leaky abstraction, as we know, right? It promises that everything will be the same, but it's not the same. And you hit different kind of corners on different machines. The same browser, the same everything, but like because we want to squeeze as much as we want. So that's why that's kind of leads into the point. Training in browser, I don't think it's pragmatically useful, right? Like train the model, but deployment in browser, inference, that's what's important. And then deployment and inference, how large is even a BERT model? Forget about GPT-2 or 3, and then you need to download it. You need to try to get it run, and think about the papers that we read about large networks from Misha Belkin, especially over-parameterized models. With over-parameterized models, they're hard to download, they're hard to run in this. So this kind of environments, I think, where we will reconsider our current flow of the whole field and think back again to inductive biases, because with inductive biases or biasing, we will be able to, which what Mohamed is doing in his project, we will be able to have very, very small models that do as well as those large models on the GPU. But for that specific task, it's not as generic or anything. But so I think with let me make random, unwarranted predictions that the renaissance of inductive bias for the models will be in the browser or on the edge computing, because that's where we can squeeze out as much of the models as we can. Look, our 22 kilobyte model, or is it 22 kilobyte model, performs as well as 2 gigabyte model. It's parameters, parameters, weight, and size. And so we can run it in browser now. But no one is against that. Protest.
Yeah, that's what,
yeah. I'm protesting. Why large GPUs? Yeah, okay, well, anyways, thanks a lot, Mohamed. I'm stopping the recording.
I feel like you probably avoid a lot of headaches by doing a lot of stuff.
Okay, but not stopping yet, something interesting.
I feel like you could avoid a lot of developer headaches by doing most of this on the server side. Like, unless you absolutely can think of a reason to do it client side. Like, if you're just making a demo, like, you could avoid all of the compatibility problems by doing like your inference server side. But I know that like defeats like the purpose of this talk, but I'm just saying like a practical thing. Like if you made like a server side call and sent your data and it's like feasible to do so, and then you did your processing server side, you could probably avoid a lot of headaches. If there are headaches. I mean, if this stuff is seamless, like it already, then I wouldn't worry about it. But my guess is it's not. That's how it usually works out.
That goes against the conventional wisdom of the web, because that's how we done it.
The conventional wisdom of the web is like it's like a standing wave. They like perpetually go back between server side, client side, or server side, client side. Like you'll hear like there was years where thin clients were the thing, and then there'll be years where thick clients are the thing. This is kind of like a thick client type idea. And a lot of it has to do with like, is the network capable of handling like sending all the data or not, or do the companies want the data or not, and things like this. But like if your REST or REST call to the server that sends the data, it's like lightweight, and you can do it on the server, then it might be worth considering. Although that can be have its own headaches.
Privacy is like it depends.
Yeah,
basically what you're saying, it depends.
It depends. But a lot of it depends on how good these frameworks are at duplicating what you can do on the servers. Like, I just imagine like if they're in their infancy, that like there's like some models that don't work, some API calls, some lines that aren't fully implemented servers in the JS framework and things like this. And that will like some of that can be some of the most frustrating things as a developer to deal with. It's just like making sure that like you have compatibility in coding and like between like library versions and like things like this. So like if you're trying to get a demo out the door, and you have like 30 frameworks to choose from, that can get frustrating. If like nobody has an answer about whether it'll be compatible, I would be afraid because you can spend a lot of time trying to figure that stuff out.
So yes,
I'm just sharing my nervousness is because like like until there's like some standards that like everybody knows what's best, then you're kind of as blind as everybody else on making your best choice on what to do.
So actually, there is like like some application that we are using server side because we cannot doing it in client side. I'm talking about this application specifically, but there is an application that you must use server side for sure. You cannot. There is a database you are using in the background, like Amazon or whatever. Here, yeah, there is a back end must exist. But for the computation of machine learning, sometimes that you are using the server side only because it's really a challenge to make it in the client side. But if you can make it in the client side, it will be better for you in order to have a peace of mind in the cost of the server that you want to install and maintain in this case. So this is actually one of the main factor that make maybe client side, if it is get much more improvement in the terms of utilizing the hardware. It can actually be like a very, very good environment to solve a lot of this problem.
Yeah, I mean, I think that that's probably true, but it really depends also on the business needs. Like if you're deploying, if you're a small organization that doesn't have resources for a big server, and you plan to have multiple clients, then client side definitely the way to go. Or if you have privacy issues, client side's definitely.
Well, think also about in the field workers as well, where connection may get spotty and things like that, and you have your tablets that you need to work. Like that, it's very complicated, depending task specific, basically.
Yeah. So
engineering, typical engineering.
Yeah. It's just worth discussing because like. If all you know is a hammer, everything looks like a nail kind of thing, like it's worth pointing out like there might be some reasons to still do things server side and stuff like this.
Sure. Everyone is correct, even though the opinions are orthogonal, but they're still all correct. Yeah. And thank you, Usman. You scheduled for next meeting. Please post the paper. The paper is not in the call. I don't know what we're discussing next meeting. Otherwise, thank you everyone for coming.